Okay, so we've been discussing for a while decoding, and we discussed discriminators and estimators, and we focused on some general limits of how well a decoder can do, and we focused on decoders which in some cases are optimal, such as the MAP and the maximum likelihood decoders. And what we're going to do now is consider a situation in which we constrain the architecture of the decoder. So the decoder is now cannot do any possible calculation, but it can do a particular calculation, and we'll discuss linear decoders. I will explain what that means in a moment. But it's a more general, it's part of a more general discussion in which we sometimes want to ask, say, how well can a linear network, or sorry, not a linear network, a neural network, how can a neural network perform decoding? And we have some constraints on the architecture of the neural network. But again, we will discuss the most simple kind of calculation that we can think of, which is a linear calculation. So what does that mean? Our situation is that we have observations. This might be the spike counts from some neurons. And in general, we have some probability distribution for these distributions given some parameter that we want to decode. And a linear discriminator will take these observations and sum them up with some linear weights. So sum over Wi are the weights, Ni plus some bias, B. And it will just take this and threshold it, and based on that, it will decide between the two options.
Can you please write
Yes, I will. Yeah. So this is what a discriminator will do. I will need to be here for a moment, and then a linear estimator. You cannot see here. Okay, so linear, and here it's okay? Here? Okay, I will do it here. Just a second. So actually I will do it here. And then a linear estimator. When we discuss a linear estimator, we will think of one unit that, one sum of this form, which maybe can be implemented by a neuron, and that will be the estimate. So we'll have sum over W, sum over I, sum here is also over I, Wi, Ni plus B, and this will be the estimate. So it's really a very simple calculation. And what we want to understand is how well these types of decoders can do, and how to set them up, how to choose the weights that will provide the best performance. So let's first discuss discrimination. And we haven't specified yet everything that needs to be specified. Most importantly, we didn't specify this. So we will work with a model that we discussed already, which is independent Poisson neurons. So that means that Ni, the mean of Ni, is some function of eta for each neuron. This is, if you want, the tuning curve of each neuron. And if you want to write the log likelihood, or sorry, the log probability of n given theta, what would that be? So first of all, it's a sum over logs of the individual neurons, because we assume that they are independent conditioned on the stimulus. Okay. And we need to write the log of the Poisson distribution. We've done that already. So it's going to be sum over I minus fi of theta plus ni log fi of theta minus log ni factorial. Okay, now we know that an optimal discriminator just needs to, if the prior is equal, needs to compare the likelihoods and choose the option with the largest likelihood, right? If there is a non-equal prior, there's a small correction that you can work out for yourselves if you want to. I will assume an equal prior. So an optimal discriminator under the assumption of equal prior is the maximum what we call the maximum likelihood discriminator. And this is just thresholding delta log L, which we defined previously. It's a difference between log L for the two stimuli that we're trying to discriminate. So this is really, let's write it in more detail. Delta log L is log P of Ni given theta 2 minus log P of Ni given theta 1. And now, if you look at what we actually need to do, so we need to take this expression for theta 2 and theta 1 and take the difference. So for one thing, this term will just fall, right? Because it's the same, it does not depend on theta. So we will be left by a term that involves these terms and a term that involves these terms, and I will write them. And I will start actually with the second one. So we have sum over I, Ni, and then we have log fi of theta 2 minus log fi of theta 1. And then we have also a minus sum over I fi of theta 2 minus fi of theta 1. Okay, what did we find? Why have I been doing this? What does this result tell us when we look at it? Remember, we're looking at some function of the ni's, which we're going to threshold. Now we're going to threshold this. If it's larger than 0, we're going to say that it's theta 2. If it's smaller than 0, we're going to say that it's theta 1. So what can we say about the discriminator that we've just derived? How does it depend on the ni's? What kind of function is this of the ni's? It's a linear function. So in fact, we derived the optimal discriminator for this problem, maximum likelihood, but it has exactly the form that I presented when I started the discussion. It's a linear discriminator. You sum up the observations with some linear weights. These are the weights. Then you add something, this whole sum, and then you threshold and decide. So what we found is a very nice result, an important result, and this is that any discrimination problem for independent Poisson neurons, for any such problem, the optimal discriminator is a linear discriminator. Okay. Now, we can also calculate the performance of such a decoder. And I would like to present now a somewhat different approach to this problem of discrimination. I will do it not fully. Part of it you will do maybe in the TA session. Suppose that I didn't know this, that if I will start with the maximum likelihood discriminator, I will end up with a linear decoder. So I would just want to start with this expression and optimize it and find the best linear decoder that I could apply to the problem. So what would I have to do? So what I would have to do is first evaluate the probability of error for this decoder. It's a function of the Wi and of the B. Okay? So our decoder, so a more general approach to this problem is to say, okay, our decoder has the form theta of x, where x is sum over I, Wi, and I plus B. And I want to evaluate the probability of error. So I know fairly easily how to do this under certain assumptions, similar to things that we've already done. When we have many neurons, or many spikes, so many spikes is actually the situation of a large Ni. Under these conditions, the Poisson distribution becomes similar to a Gaussian distribution. Another way to think about it is that we have the sum of many independent observations. Also, then we sum. So these things are, when it's not sufficiently large, each one of them is distributed as a Gaussian distribution. But then we also sum many of them. So this might also help the Gaussianity. So let's just assume under some conditions, X becomes distributed as a Gaussian. We're going to analyze the problem only under that assumption. So this is of course an approximation. So if it's a Gaussian, we want to ask how is it distributed. All we need to know is the mean and variance. So it's fairly straightforward to evaluate the mean of X and the variance of X. What do we need to evaluate it for? We need to evaluate it only under the two conditions of theta equals theta 1 and theta equals theta 2, because these are the two we're considering now. There's just discrimination between these two stimuli. So we need to do this for theta 1, theta 2. And then, basically, if we would plot, okay, we'll do this over there. If we would plot how X is distributed, then we will have some distribution P of X given theta 2. We would have some distribution, no red, okay. We would have some distribution P of X given theta 1. And we know that our discriminator is choosing, if X is larger than X, if X is larger than 0, it's choosing our discriminator is choosing theta 2. If X is smaller than 0, it's choosing theta 1. And so, for example, what we want then is the probability of error if it's theta 2 is this area, and the probability of error if it's theta 1 the probability of error if it's theta 1 is this area, and the probability of error if it's theta 2 is this area. So we can calculate these quantities and find the probability of error. right? So we can, by calculating these quantities, we can find the probability of error. We can get an expression for this. And then we can minimize this expression with respect to the parameters. The parameters of x are the wi's and b. So we can minimize with respect to wi's and b and get the linear discriminator that minimizes the likelihood of error. And then we'll have the, at least under these conditions, we'll have the likelihood of error of the best linear discriminator. And of course, it will have to agree with the error of the maximum likelihood discriminator, because we know that the maximum likelihood is a discriminator, is a linear discriminator. So that's one comment. Another comment is that if we go back to what I discussed here, the maximum likelihood discriminator and the fact that it's linear, in fact, you can generalize this to discriminating between any set of possible stimuli. So, in some sense. So, if you have just theta 1 and theta 2, you need to compare this and this. It's a linear function of the spike counts, and you threshold. What do you have to do if you had 10 possible stimuli and you want to choose the one which is most likely? So you could compare all two, or you can just calculate the whole 10 likelihoods and choose the one which is most large, right? So this would not be a decoder which has the simple structure that we discussed, where you just you calculate one thing which is this difference and threshold it. So imagine that you have 10 stimuli. You want to discriminate, you know that there are 10 possible stimuli. The likelihood is the likelihood to get the observations given the stimulus. Right? So you have now, suppose that you have 10 possible stimuli, you can calculate what is the likelihood that you observe, and then choose the one which is most likely. And you have a prior, you could correct for the prior also. Okay, so...
So the pressure you do the likelihood.
So, but what my claim is that even that, you can think of some interpretation as maybe a neural computation. Why? Because you can imagine that you have your inputs, N1, N2, N up to N, okay? And then you devote one neuron to calculate the likelihood of each possible stimulus, okay? So this neuron will calculate log P of N given X1. This neuron will, theta 1. This one will do log likelihood of N given theta 2. This one will do log likelihood of N given theta M. Let's suppose that we have M stimuli. So each one of them, the kind of calculation that it needs to do is a linear function of the spike counts, except for this term. But this term doesn't matter because it's the same for all of them. So we can just throw it away. So if we just make each one of these units calculate this linear function of the Ni's, we now need to pick up the one that has the maximum activation. So the architecture that this suggests is something like this. This connects to, all of them connect to this one, all of them connect to this one, and then we need to do some highly nonlinear calculation in this layer, and in some sense pick up the one which has the largest activation. I'm not going to devote more attention to this, but it's just it's interesting to think about it, that you can have this form of readout that picks up, that implements the maximum likelihood discrimination. Okay, now this is what I wanted to tell you about discrimination, and now I want to switch to estimation. So, in some sense, you could say, well, based on what I've just told you, you could do an estimate by having a huge number of units like this and calculate the likelihood of each possible theta and just pick the one which is most likely. But we're now discussing a much more simple architecture, which was what I started with, where we have one unit And all that unit knows to do is to sum up the spikes, the observations with some linear weight. And we want that to be the estimate. So we're discussing now a linear estimator. And our estimator has the form, the estimate is sum over I, Wi, Ni plus B. What can we say about such an estimator? So the first thing I want to do is to try to go along the path that I went with the discriminator and not consider this particular architecture, but write down the maximum likelihood estimator for Poisson in the specific case for Poisson neurons. And let's see if that leads us to something like this or not. So let's consider the maximum likelihood estimator for Poisson neurons. Independent Poisson neurons. So if we would want to write down what does that estimator do, it needs to pick up the theta for which the observations are most likely, and we can write that mathematically as argmax on theta star log L of theta star, right? Okay. So if I want to express theta star using this and log L, we had it. Let's write it down. So it's argmax over theta star of sum over I. We had minus Fi. So minus Fi of theta star plus sum over I Ni log Fi of theta star. And I will actually not write the next term, which involves the n factorial, because it does not depend on theta star, so it does not affect the argmax. So I can finish this here. So if I want to now mathematically extract from this expression what is this estimate, the maximum likelihood estimate, what do I need to do? What kind of equation theta hat obeys? Exactly. So I know that it's the maximum of this. So, okay, maybe there's more than one maximum, but at least it has to obey the equation that the derivative of this expression with respect to theta star at theta hat is 0. So let's write that down.
Then you know that Fi is bounded, because probability distribution is bounded.
Yeah, Fi is a tuning curve of the neuron. It's okay, so d to the theta of log L at theta equals theta hat, if you want, or theta is 0. And that means that sum over Ni, I'm starting with this part, Fi prime of theta hat divided by Fi of theta hat minus sum over I Fi prime of theta hat is 0. This is an equation which is obeyed, an implicit equation which can be used to determine the maximum likelihood theta hat. But what you see from this exercise is that this is a highly nonlinear equation. It involves, these functions of theta hat, which are not linear functions in general. So it's a highly nonlinear equation. There's no reason to think that the solution of this equation is a linear function of the Ni. Okay? Not linear in Ni. So even for this case of independent Poisson neurons, for which the maximum likelihood discriminator was a linear discriminator, the maximum likelihood estimator is not a linear estimator. So that's just a, we don't have this nice property, but nevertheless, we can find, we can optimize, yes?
It's not linear in Ni, but regarding to Ni, it is.
Well, this expression, so what is, this expression is linear in the Ni, but the solution of this equation, theta hat, is not, because it involves these highly nonlinear functions, possibly highly nonlinear functions of theta hat here. All right. So that didn't lead us to this path didn't lead us to the best linear estimator or to some form of linear estimator, but we can just optimize the linear estimator for some cost function. Okay. So let's do that. Yes.
A bit lost the logic of what you're trying to achieve right now.
Okay.
Trying to find.
Yes. So the part on the discriminator is okay?
Okay.
Yes. Okay. So now for the linear discriminator, because for the linear discriminator, I showed you that the maximum likelihood discriminator is actually what I call the linear discriminator. Okay? And therefore, when we were considering the estimator, I decided, okay, let's see whether also maybe the maximum likelihood estimator is linear. But it's not. Okay? So now we have to go with the other approach for the estimator, which is just to optimize it. And that's what we're going to do now. So what I'm doing now is a general optimization of a linear estimator. I think that I need to replace this pen. Wow. Okay, here's a good one. So let's reformulate the problem again. We have our observations. N. Warning, in my notes for some reason it's now R. So if I write R, shout and tell me I need to correct it to N, but there's no reason to use a different notation than before. So we have P of N given theta, and our estimator is sum over I, Wi, Ni plus D. And our goal, we want to optimize this estimator. But what does it mean to optimize it? What are we going to optimize? Yeah, yes, that's absolutely correct. What I'm free to tune is the W, I's, and B. But what is my goal? Okay, but what is the error? I need to decide about it. It's in contrast to discrimination, where it's clear it's probability of error. Here, I need to decide on a measure of a cost measure. Sometimes it's called the utility function. How do I weigh errors? And we'll discuss mean square error. Mean square error. So I will write this as the average of theta hat minus theta square. And this is averaged over what? It's averaged over two distributions. One is the distribution of the responses, which are conditioned on theta, but also this is averaged over the distribution of theta. So the general distribution from which theta is being drawn in each time we need to do an estimate might matter. It will matter. Okay, let's write this in more detail. This is an integral over theta, p of theta. And then there's an integral over, this is an integral over the responses. This is a high-dimensional integral of the responses of each one of our, say, neurons, p of n given theta. And then it's what our estimator spits out when we give it these particular n's, minus the true theta squared. All right. So now this is what we need to calculate. And I'm going to focus on this part now. I'm going to focus on this part, and we need to write a mathematical expression for it. So the theta hat is this thing, right? So we need to calculate. Okay, I will keep it within these. I will not write down explicitly these integrals. This was just to explain clearly what is meant by this averaging, but I will go back to the bracket notation for the averaging. So I have here sum over I going from 1 to n, where n is the number of neurons. Maybe I should write it also here. I goes from 1 to n. Sum over I, wi, ni plus b minus theta squared. Right? And again, when I write these brackets, it means actually this whole integral. Okay, now what I want to do is we have a square of a sum. So I want to re-express it as a square of different type of terms. In general, what kind of function of the ni's will I get here? It's a quadratic function. It will involve three types of terms. There will be terms which are quadratic in the ni's, which involve two ni's. There will be terms which are linear in the ni's, which will come from one of these combined with this. And then there will be some constant. So I want to write each one of these terms explicitly. So I will have here, and I will already, so I will have here the following. And now remember also that the wi's and the b are just constant. For the sake of this calculation, they are constant, meaning that they don't depend on theta and n. So when we do the averaging, these are just numbers. Okay, so I will have terms that looks like sum over I and j, wi, wj. And what will these terms be multiplied with? Ni and j, but this I need to average because ni and j is a random variable. So here I have ni and j within these brackets. Then I will have terms which are a sum over I, wi. And what will wi be multiplied with? Yeah, so we'll have two types of terms. We'll have terms which I will write them separately. We'll have terms that will involve the b and terms that will involve the theta. And I will start with the theta. So I have here sum over I, wi. Now I need to do the average of ni times theta. Both theta and ni are random variables, so I'm putting them both inside this bracket. And in fact, there's a 2 missing here. right? Because we have all this thing multiplied by itself, so I can take the ni from the first expression and the theta from the second, or I could do vice versa. So that's why there's a 2 here. Okay? And now we also have these terms. So in these terms, it will be, again, there will be a 2, and there will be a sum over I. B is not a random variable, so I don't need to put it in. So let's just put wi here, and then there's a b. The b I don't need to put inside the average, but I do have the ni, right? And then there will be terms coming, the terms that don't involve the n. So one of them will be just b squared. Another one will be minus 2b average of theta. And another one will be the average of theta squared. Okay. Now, what do we need to do with this expression? Well, we want to find the optimal w. So we want to minimize this, right? So we're going to differentiate, and I'll start by differentiating with respect to b. Okay, our parameters are all the wi's and b. So I'll start with b because it's just one number. So d to the b, the partial derivative with respect to b of the error is the derivative with respect to b of all this expression that I wrote here. And, well, not all the terms here depend on b, so we only need to look at the ones that do. It's this one, and this one, and this one. So, it's 2 sum over I, wi, ni average, minus 2 average of theta, plus 2b, and that is 0. And so from this you see that what we get is that b, the optimal b, is equal to the average of theta. This is just a property of the prior from which the thetas are being drawn. And then, how can I write in a somewhat nicer way this thing? Slightly nicer. In the product of 2 vectors. So this is, the average response of the neurons multiplied by the weights. I didn't yet specify the weights. We need to find them. But once we find also them, this will be the bias term. And one of the, before we even continue, one of the interesting implications of this, or thing to note, is that if we ask ourselves the following, suppose now that this is our estimator. So suppose that we give our estimator inputs which are precisely the average inputs. So here I will put for each n I will put its average. If n is a spy count, maybe we can't do it because the average might not be even an integer number. But nevertheless, suppose that I give this estimator the ni's which are the average ni's. What will it spit out as an answer? So I put here the average ni. Yeah, right? You see that? If I put here the average of AI, I get W transpose Ni plus B, but B is average of theta minus n times w. So these terms can cancel. So if I happen to give the estimator as input the average ni, it will spit out as an answer the average theta. Just something to notice. Okay. Now we need to find also the weights. So let's do that just before the lesson ends and hopefully get the answer. So we need to do a partial derivative with respect to yeah.
And why would it spit out the theta?
I don't know. This is what it does. We see it from the formula.
Like, what do you insert? You insert
Well,
the same.
if the sorry, yeah, I wrote here ni without average. I did write average, but yeah, no, that's fine. So I'm just saying, if the input that I give to the, let's write it like this. If ni happens to be, if the input that I give to each one of the, from each one of the neurons, is what it spits out on average. Average over the whole, average over theta, average over the distribution of ni given theta. If I take just the average response of the population and give that as input to this estimator, it will spit out as an answer the average theta. Okay? Kind of makes sense that it's a sensible thing to do, but it's a mathematical property that you can see from this solution. Okay, but we didn't find the solution yet because we just found B. We need to find also the wi's. So I write down that the partial derivative is 0. Now, what is that partial derivative? So the terms that involve the w's are this one, this one, this one, and that's it. So from this term, what will I get? I will get 2 times sum over. So if I want to okay, I will not even write the 2 yet. If I want to take the derivative of this with respect to wj, with respect to wi, right? I'm taking the derivative of this with respect to wi. What will I get?
So for every time that j is not I, you get wj.
Well, even if j is I get wj. Right, so I have here wi multiplied by sum over all the j's, wj, ni, and j. So I have here sum over j, wj average of ni and j. And is this the answer?
No, because it can also be.
Yeah, exactly. So I took the derivative with respect to the possibility that this one is the I that I'm interested in, but it might just as well be this one, and because of the symmetry of this expression, I will just get the same thing. So there's a 2 here. This is one term. And then here, the derivative with respect to wi is simply minus 2 ni theta. And here I have 2 times b times ni. And this is 0. Okay. So let me write this a little bit differently. Sum over j ni. First of all, the 2's go away. Ni and j, wj. And then I will put this term minus ni theta, and then what I will do next is that I will use the expression for b. I know already that b is this thing. So here, remember the 2's I already divided by, so I will have one term which is plus theta ni. Right, this is this multiplied by this, and then this itself is a sum over j, nj, wj, and this is multiplied by ni. So I will have here minus sum over j, ni, nj, Wj. Okay. And when I say it in words, I say Ni and J, it's important whether the averaging is on each one of them separately, as it is here, or here it's the average over the product. So let's just write down the equations and we'll discuss them on Tuesday. Just write them a bit more neatly. First of all, you see that we get here a linear set of equations for the W's. And so, because it's a linear set of equations, a priori we know we can write it in the form of a matrix times W minus some vector is equal to 0. It's a linear set of equations. And now let's just read out from this expression what is this matrix C and what is this vector U. So the matrix Cij, the ith element of the matrix C, what is it?
The average over the multiplication.
Yes?
The average over
Right. So this is Ni Nj minus Ni Nj. In other words, this is a covariance matrix of the responses, the inputs to the neural responses or the inputs to our estimator. This is a covariance matrix of N. And the UI, what are the UI? It's this thing, right? It's and because I put here a minus sign, it's Ni theta minus Ni theta. In other words, this is the covariance of theta and the responses. Yeah. Okay. So this is what we got. We now have a full solution for the optimal estimator. The weights are the solution of this equation, where this is the matrix, this is this vector, and the B is written over there. Okay, and we'll discuss this, continue to discuss this on Tuesday, what this means, what these equations tell us.